This is part 2 for lesson 3.3, linear and exponential equations. The next problem, it says the price of milk has been rising with inflation at 3% per year. So 3% is my rate of increase. And so that's going to be the 3%, which would mean 0.03. Remember, you move that decimal 2 times to the left. The rate, or my growth factor, that's going to be the 1 plus 0.03, or the 1.03. So that's the B. It says the price was $2 per gallon 3 years ago. What is it now? So again, we're kind of thinking about like, I need to know now. I know what it was here. It was $2 a gallon, and this was 3 years ago, so at -3. So I can write an equation that just says, if I start at $2 and it rises at 3% for -3 years, that's going to back it up. And so then I can do that calculation and find out. Now I'm expecting that it was less 3 years ago because it wouldn't make any sense if it was more because it's supposed to be going up. So when I do the math on that, put it in my calculator, it comes out to y equals $1.83. And so that means that it was $1.83, and then it went up 3%, and then it went up 3%, and now it's at $2. So that's what that means, and so that makes sense. Now that's not the only way to do that. The other way you could do it is say it's $2 now. I don't know what it began with, but it's going to grow at 3% a year for 3 years. And so then you would divide by 1.03 to the third power. And that's going to give you exactly the same thing. That will give you the $1.83. Okay, what you don't want to do, because this will not work, you cannot say I'm going to do $2 and I'm going to do 1 minus 0.03 for 3 years. You can't take off the 3% because remember, a percent is a percent of something, and so you're doing a percent of something different here. So if you do that, you'd have 2 times 0.97 to the third power, and if I did that, I'm going to get $1, well, it's 0.825, so it would round to $1.83, but if the numbers were bigger, you'd see a bigger discrepancy. So you would get lucky there, but that is not the same thing, so that's not going to be equal to what happened up there. This one came out to 1.83028. So I know that in terms of money, that's not hardly any difference at all, but that is showing that it's not the same thing. Okay, let's go to the next one. Number 18, it says write the equation that represents each table. So here we're going to write some equations. So we're going to tell if it's linear or exponential. How can you look at a graph really quickly or a table really quickly and tell if it's exponential? I want you to look at the two tables and just notice similarities, differences. Look at the x's. The x's are the same. So focus on the y's. What do you see that's different that would maybe help you identify quickly which one you think would be linear and which one you think would be exponential? Do you notice how these are just staying like pretty consistent? Like they're not blowing up. These are going out, like they're getting much bigger faster. And so that's one thing that I notice visually as I look at tables like that. It kind of draws my eye that these are getting so big so fast, and so I'm thinking that's going to be exponential. Now of course that's not a way to tell for sure, but it just kind of gives me a clue. So what I'm going to do is I'm going to first make sure I am right about that. So this first one I'm going to go up 2, up 2, up 2. So it looks like every single one is going up 2. So that's increasing by 2 while this is increasing by 1. And so my slope is going to be 2 over 1 because rise over run, y over x. So my slope for this one is 2. My y-intercept, I don't see that on the table because it doesn't have a 0 right there, but I can back it up and say it was 0 because that's what that would be. So my b would be 0. So for this first table, my equation is going to be y equals 2x plus 0. That's the equation that matches that table. I can double check that by taking just a random number. If I plug in 5, do I get 10? Yes. And so you can do that to make sure that everything works. But this one is linear. The first table is linear. The equation is the y equals 2x, and that's how I found that. So you find the slope, and then you can find the y-intercept. Okay, looking at the second one, I see I can add 2 there, but it doesn't keep working for me to add 2. So I have to figure out something different. Now these numbers are pretty easy to tell, but what if it was hard to tell what you do each time? You could say 32 times something has to be 64. So what is that? You divide both sides by 32 and you get x is equal to 2. So this one over here on the right, it has a rate of 2. My rate, or my b, is going to be 2 because it's doubling every time. Now that's obviously not the same as having a slope of 2, because a slope of 2 gives us something different. So it has a rate of 2, so that's going to be b. Again, I need to back up to find out what is 0, what is my y-intercept, so what does it start with? So instead of multiplying by 2 every time, if I go backwards, I divide by 2. So 2 divided by 2 is 1. So to write my equation, y equals a times b to the x, I'm going to write y is equal to a as my initial point, and that's the y-intercept. That's going to be 1 times 2 to the x power. Now if you have 1 as a number right there, you do not have to write it. You can just write it like that. Although on this type of problem, I do not think it's a bad idea to put the 1 there because it helps you easily identify, there's my y-intercept, that's my rate, it's going to double every time. When you go to graph something like that, it also helps because you can say, here's my y-intercept, so I know I'm going to be right there at 1, and it's going to double. So then I'll go to 2, then I'll go to 4, then I'll go to 8, and so on. So it helps you graph really quickly if you know the y-intercept and the rate as well. Okay, we're going to look at a couple story problems. If you please, King, put 1 grain of wheat on the first square of my chessboard. So if you think about a chessboard, and it's got, the squares, and they alternate, usually red and black. Well, I think that's usual. So, you have like this. Okay, so this, let's see, the inventor is saying put a grain on the first square of my chessboard. So we're going to put a grain on the first square of the chessboard. Then 2 grains on the second square, and then 4 grains. This is actually, if you look at it, this is actually this table right there. So by the time I got to the 10th square, we'd be putting 1,024. So, down here it'd be like 1,024. So, good luck making that many dots there. So, anyway, see, 8 grains on the 4th square and so on. The king gladly agreed, thinking the man a fool for asking for a few grains of wheat when he could have had gold or jewels. The king never finished paying the inventor, and according to legend, instead had him beheaded. So explain why the inventor was beheaded. Well, obviously, it's because it just got too much too fast. And so if you're thinking about, by the time you got to how many squares are on a chessboard, which I think there might be like 64 or something. You guys probably know better than me. But let's just say that there are 64. And so if we said we're going to start with 1 grain of rice and we're going to double it each time, and 64th power, how many grains of rice is that? So you put that in your calculator, and it's just a huge amount. You see that I put it in my calculator, and it says 1.8446 and some other decimals, and it says E19. What that means is my decimal is going to move 19 places. So you're looking at billions of grains of rice, even more than that. And so that's why it was worth more than gold and jewels. Okay, so just, that much wheat. And, so I guess that would be why. So basically the idea, as far as your explanation, is that it just got to be too many, and it was not possible to do, and so that would be why. Okay, next question. A leprechaun promises you fantastic wealth and hands you a penny. Okay, so you have 1 penny. You place the penny under your pillow, and the next morning, so you put it under your pillow, and the next morning you have 2 pennies. The following morning, 4 pennies, so another night, and then you're going to have 4 pennies, and so on. So this is like the grains of wheat in a previous problem. So what's happening, it says each magic penny turns into 2 magic pennies. So how many nights must you continue to have $10 million? So if you think about 1 penny, now, first of all, pennies are cents. 10 million is dollars. And so we have to decide, do we want to talk about this problem in dollars or in cents? If you tried to convert $10 million into how many cents that was, that's going to make it even, more zeros to deal with. So let's take the penny, and let's say we're going to start with 1/100th of a dollar. Okay, and it's going to double every day. So that's the situation. Now it says I want to know how long does it take, so that means I don't know the time. How many days is it going to take for this to happen? But I want my end result to be $10 million. So I'm going to put 10 million right here. And I have to figure out how many that is. Now, right now, we do not know how to solve for an exponent. That's something you won't learn for a couple of years still. But as far as a problem like this, we can try to figure it out. One thing you can do right here is you can divide by the 0.01 and get that out of there. So if you take 10 million and divide it, by 0.01, that is, I'm not even sure how many zeros. It's going to be, and then 2 more, I think. So 9 zeros, I think, is what I should have, yeah. And that's going to equal 2 to the x power. So that's 1 trillion, let's see, no, 9 billion, 1 billion. And so I cannot just divide by 2. Dividing by 2 doesn't work here. I'm going to, at this point, you're going to have to just guess and check some numbers. So I know it's not going to be 2 to the 64th power because we tried that in the last problem and that was way more than 1 billion. So try something smaller. So just start trying some numbers like maybe 2 to the 15th or 2 to the 12th or something like that, and try some numbers and find out about how many nights will it take. So pause the video and try some numbers and find out about how many nights it's going to take for this to happen. Okay, so I tried a couple of numbers. So I started with 2 to the 15th, and that was only $32,000. So it wasn't like it was nothing, but that wasn't anywhere close to a billion. So, or what am I looking for? Yeah, I'm trying to find when is it a billion. So I did 2 to the 20th, and that's over a million, so we're getting there. 2 to the 25th was 33 million, and then some. 2 to the 30th puts me at over a million, over a billion. So that's over a billion. So it's 1,073,741,824. So the question was, how many nights does it take? So for sure by 30 nights, you'll have over the billion. Well, hold on. You'll have over the 10 million. We had to find the billion because we divided by 0.01. So I'm just saying 2 to what power puts me over a billion. So I need to say, what about 2 to the 29th? Would I have a billion there? So do 2 to the 29th, and I find out that there I've got only 536 million. So not quite what I need. So definitely that one extra day is going to change it. So by 30 days, that's what you're going to need for this. So I'm going to come back to the original problem. And I am going to take my equation here, and I'm going to say, all right, if I start with 1 penny, and I go 2 to the 30th power, when am I going to have, I'm not going to get exactly $10 million, but by day 30, I'll have just over $1 million. Or $10 million. Yeah, $10 million. So you can just make sure that that really works. So 0.01 times 2 to the 30th power, and I get, like we saw earlier, I get $10,737,418.24. So anyway, that's how you do something like that. So like I said, at a point later, about 2 years down the road, you'll learn how to solve for an exponent, but you cannot do that now. You just don't have the tools to do it. So remember, you cannot just divide by 2 there. That does not work that way. So at this point, it's just kind of a guess and check. Okay, the next and last question. Suppose you place a single bacterium in a bottle. Okay, so let's think about, we've got this bottle and we've got this one lonely bacteria. And that's at 11 a.m. It grows, and at 11:01 it divides into 2. So at 11:01, so just 1 minute later, we've got 2. So that's 11:01. And so it's going to keep doubling. So the 2 bacteria grow, and at 11:02, I'm going to have 4 bacteria. And so they grow and keep going and so on. So we're starting with 1, it's going to divide, we're going to get 2, and then we're going to get 4, and then we're going to get 8, and so on. So the question is, if the bottle is full at noon, how many bacteria are in the bottle? Okay, so let's think about how many minutes has happened between 11 a.m. and noon. So that's 60 minutes. Okay, so we know that the equation is going to be, we're starting with one bacteria, it's going to double, and we're going to do that for 60 minutes. So how many bacteria is that? So 2 to the 60th power is what I'm asking. Now you put that in your calculator and it gives you this scientific notation, so 1.1529. So if you haven't put that in your calculator, I want you to do that. So this is what my calculator says, and that means that I'm going to move this decimal 18 times. 1, 2, 3, 4, and then I have to fill it in with zeros. 10, 11, 12, 13, 14, 15, 16, 17, 18. So the number is very, very large. And the reason why we have scientific notation is because sometimes in science we're dealing with very, very large or very, very small numbers. And so in order to be able to write them a little more efficiently, we have scientific notation. So let's see, this is millions, billions, trillions, quadrillions, quintillions. So 1 quintillion bacteria and then some. So that's a lot. So if you have this jar full of bacteria, that's what that would be. I did look it up once and I did find out that actually you can have pounds of bacteria. So that sounds really gross, but that can happen. So the next question is, when was the bottle half full? So I want you to stop and think about that. If the bottle is full at noon, at what time was it half full? So write down what you think, pause the video, write down what you think, and then come back and see if you're right. Okay, the correct answer to that was it was half full at 11:59, because then it doubled and now it's full. So half full at 11:59 a.m. and in the next minute it was full, because that's what doubling does. Okay, 23, it says, if you, a mathematically sophisticated bacterium, warn of impending disaster at 11:56, would anyone believe you? So at 11:56, how many bacteria were there? So you can find that out by putting in your equation 56 minutes. So 2 to the 56th power, is that really so different that nobody would believe you? Well, at 11:56, actually, let's think about maybe not the number of bacteria, because that's really hard to conceptualize. But let's think about it. If we have a full bottle at noon, and then at 11:59 it was only half full, and at 11:58 it was only a fourth full, and at 11:57 it was only an eighth full, and at 11:56 it was only 1/16 full. So thinking about it like that, it makes more sense. Like, nobody would think that that was a problem. And so that's one of the things about exponential growth, is that at the beginning, it doesn't seem like much, but it gets out of control very quickly. And so that's why when we're looking at exponential growth of things, that's why it's dangerous. Earlier this year with COVID, when they were talking about flatten the curve, and they were saying that, we don't want this to grow exponentially, because then that's where it gets out of control. And so that's back, in March of 2020, they were saying flatten the curve so that it's not growing exponentially. So that's what that was talking about. Anyway, so exponential growth can get really big really fast, and so that's what we're doing in this problem, is just exploring that idea. Okay, you should now be able to do your assignment. So you're going to be determining if situations are linear, exponential, or remember that neither one is an option, but be really careful. I'm not going to put very many of those out there, because then you wouldn't have to do anything with it. If it's linear or exponential, you would need to write an equation. So remember that the linear equation, you need the slope and the y-intercept. For the exponential, you're going to want the initial value, or the y-intercept, and the rate that it's growing, and then add that to 1 so that you'll know what the rate is. So you should be able to do that, and then you'll have to do some story problems where you apply that.